Who is there from NPTL?
Bharat, sir.
Bharat.
Yes, sir.
So nobody has joined. What to do?
We can end the session, sir.
Or wait for another 10-15 minutes?
Yeah, fine, sir.
Because suddenly some people may join late.
Yes,
We
sir.
will wait up to 11 o'clock and then call off.
Okay, sir.
Huh? Okay, thank you. Hello, there was a message from Govinda Varadi who wants more basic applications of NMR spectroscopy. Of course, in this course, we are covering a lot of concepts and applications of one and two dimensional NMR. But if any of you is interested more exposure to this field and learn more about NMR and its applications, you can attend NMR workshop that are organized on NPTEL Plus platform. That I'll organize once in a year or so. And also workshops will be conducted with different places occasionally. We keep doing. Next month on October 6 to 11, there is an NMR workshop at Mahe, that Manipal Academy of Higher Education. If any of you is interested, please attend. You'll get more exposure in that. Thank you. Anybody has any questions? Those who have joined now? Any specific questions, clarifications? Yeah, yeah. Participants, please ask questions if you have any. You can unmute yourself and ask. Okay, so we'll come back to. Okay, now questions have started coming. It's good that people started interacting. So anisotropic effect, I don't know what is the question, which is very clear. In fact, most of the NMR parameters are anisotropic in nature. In fact, they are tensorial. For example, chemical shift is a tensor. It is represented by 9 elements of the matrix, 3 by 3 matrix are there, and you can measure the chemical shift in different directions. It can be different. That is because that means it is anisotropic. Anisotropic means its value will be different in different directions when you measure. For example, chemical shift along x-axis could be different, chemical shift along y-axis could be different, and z-axis measured can be different. What happens is, there is an isotopic average, that means if somehow anisotropic gets averaged out, you will get an average value. Then anisotropic component will be completely removed. For example, for the molecules in the solution state, there is no chemical shift anisotropy because the random motion of the molecule, because of thermal agitation, the anisotropy effect will go. So what you determine is the isotropic chemical shift, which is the average value. Same thing can happen. Same thing you can talk about dipolar couplings also. All right. So more about this thing, I don't know if you have a specific question, please talk to me. I have given my number. Anytime during the daytime, please call me if you have any questions. And if it is a video, Zoom video or WhatsApp video, we can explain, I can explain to you so that you can understand. Now coming to the Popol notation, another question by one of the participants. I will open the folder and then I will explain it to you. Okay. Are you all able to see my slides? Okay. Since the time is short, I don't want to go into the complete class. I will tell you what is Popal notation. The Popal notation, it comes before that, you have to understand what is a coupled spin system. For example, let us say in a molecule, let us say we have 5 protons. I have numbered as 1, 2, 3, 4, and 5. One may be coupled to 2, it may be coupled to 3, 4, 5, etc. And coupling constant is always given by J. For example, coupling constant between 1 and 2 is J12. Similarly, J13, 14, and 4, etc. could be there. One of the coupling may be 0, it doesn't matter. But all these spins which have coupling among themselves form what is called a coupled spin system. The coupled spin system, the NMR spectrum, can be understood in different ways. That depends upon number of spins that are coupled, whether 2 spins are coupled, 3 are coupled, 4 are coupled, how many are coupled among themselves. That is first point. Second, whether the spins are strongly coupled or weakly coupled. There are 2 points. Please understand. There are 2 points. Spins can be strongly coupled or they can be weakly coupled. Now the next question is, what is strongly coupled and what is the meaning of weakly coupled? I'll explain to you here if you go further. For example, weakly coupled is one. I consider 2 protons, A and X. The chemical shift of these two are substantially different. That means one may come at, let us say, 1 ppm, other proton may come at, let's say, 10 ppm. What is the difference between these two? 9 ppm. In 500 megahertz spectrometer, 9 ppm corresponds to 4500 hertz. Remember, it is 4500 hertz. It's a very large chemical shift separation. So you measure the chemical, find out the chemical shift difference between 2 coupled spins. And I find out what is the J coupling. The J coupling is usually very small, of the order of few hertz, maybe 8 hertz, 10 hertz, 20 hertz, like that. That is among the protons. Where is 20 hertz? Where is 4500 hertz chemical shift separation? Now take the ratio. 20 hertz divided by 4500 is very, very, very small, much, much smaller than, it may be of the order of 0.0001 or 2, like that. Very small. So J over chemical shift difference ratio defines whether it is weakly coupled or strongly coupled. If it is very much less than 1, much, much smaller than 1, then 2 spins are weakly coupled. If the chemical shift difference delta is almost equal or comparable or much less than J coupling, then the 2 spins are strongly coupled. Remember this concept is strongly coupled. And this strongly coupled and weakly coupled spectrum are very much different. Strongly coupled spectrum of 2 spins and weakly coupled spectrum of 2 spins appear entirely different. You understand this. So, to understand the nature of spectrum, how the spectrum comes, how the multiplicity pattern come, what is the type of spectrum you are going to get when the spins are weakly coupled or when the spins are strongly coupled, there is a notation called Popal notation. Popal is a scientist who gave this notation. I will explain this to you when we go further. These are all not necessary. Okay. See, Popal notation, what we do is, each spin-half nucleus is represented by a capital letter of the alphabets here, Roman alphabets of English, A to Z. It should be in capital letters. Now, what we will do is, if there are 2 spins which are weakly coupled, that means the chemical shift separation is much larger than the J coupling. They are called weakly coupled spin system, and the spectra are called first order spectra. In such cases, we define in a different notation. On the other hand, if the spins are strongly coupled, that means the chemical shift separation between two coupled spins are very small or comparable to J coupling, we get what is called second order spectra. Please remember, for weakly coupled spins, we get first order spectra. For strongly coupled spins, we get second order spectra. And first order spectra are easy to interpret. Straightforward analysis is possible. Looking at the spectrum, I can tell you what is the chemical shift of each spin, what is the coupling constant. Everything I can measure very easily. Straightforward analysis is possible. That is for first order spectra or weakly coupled spins. Whereas for the second order spectra, first order analysis is sometimes very difficult. Okay, up to 2 spins we can manage. But beyond that, 3 spins or more, first order analysis is not possible because the spectra are strongly coupled, spins are strongly coupled. We need to interpret, we need to analyze by using numerical synthesis, numerical analysis, like using computers. Okay, but that is the convention. Now let us understand how do we define this Popper notation. Always I told you, spins are represented by letters of the alphabet. Spin half nucleus. I'm not talking about spin 1. If I say A and X, where is X in the alphabet? X is far away. If you go A, B, C, D, E, F, G, H, X is far away. That means the chemical shift of the nucleus, coupled spins, are far away, very much separated. Then we use the letter which is far away in the alphabet. That means A and X are weakly coupled. Chemical shift separation is very much different, large difference, because the letters will tell me they are separated very far in chemical shifts. This is for 2 spins. For 3 spins, same. A, M and X. M is far away from A and X is far away from M. And X is even also far away from A. That means all the 3 protons coupled here are weakly coupled. So weakly coupled spin systems are represented by alphabets which are far away. Okay. Now, for example, if I consider a spectrum like this, the A, M and X, I will call it. A and M and X means they are weakly coupled. That means the chemical shift of this proton is very much different from this, and it is very much different from this. All the 3 protons are weakly coupled. Okay, this is what it is. For strongly coupled, we use the notation which are very close in alphabets. For example, A and B, AB. AB means the chemical shift of 2 spins are very small. The difference is very small. They're very close in appearance. In the spectrum, they appear very close. That means chemical shift separation is not much. And that is given as strongly coupled, means the letters are not far away, close to each other. So AB is strongly coupled for 2 spins. ABC is even more strongly coupled for 3 spins. For 4 spins, it is like this, ABCD. So this is how you can explain. These are some of the examples. I've already explained this to you. For example, equivalent spins, how we mention is like this. Weakly equivalent spins, if it is there, we give a prime notation. We have different types of nomenclature possible. AB, for example, I have considered 2 spins. There are 3 possible combinations. A and X, Popper notation, weakly coupled spin. AB, strongly coupled. A and A prime, that means the chemical shifts are same, almost. There is no difference in the chemical shift, and their coupling is also present. They are strongly coupled. A2 is even more strongly coupled. So there is possibility is there are different types of nomenclature depending upon how the spins are coupled. For example, if I go to a molecule containing CH2, I can consider as these two protons are from A2 or X2. CH3 can be considered A3 spin or X3 spin. Like that, depending upon the couplings of the protons and chemical shift difference among the coupled spins, we can have different nomenclatures like this: weakly coupled, strongly coupled, etc. For example, you consider a molecule like this: CH3CH2OH, ethyl alcohol. Here, three protons are strongly coupled, three protons of methyl group. We call it A3. Here, two protons are strongly coupled. We call it X2. Why? Because this and this are far away separated. So we call it A3X2 spin system. You understand? This is A3, this is X2. Why not it is B2? If it will be very close in chemical shift, it will be B2. Since it is very far away, due to OH attached to this chemical shift separation is far away. Hence, I call it as A3X2 spin system. Like that, you can start talking about varieties of spin systems. We can have AB, ABX, for example. I'll take one example. Here, A and B are strongly coupled. A and X are weakly coupled. B and X are weakly coupled. Three spins are there. Two are very close in chemical shifts, and X is far away. And between A and X and B and X, there is large chemical shift difference. And this type of spin system is called ABX. I can keep on explaining this for more than 1 or 2 hours. Since the question is for discussion, we have other questions also. I am going to stop it here. But what I'm trying to tell you is Popal notation is alphabetic notation of strong and weakly coupled spin system, which dictates how the NMR spectrum appears. Okay. With that, I will go to the next question, whatever is there, what others have asked. Okay. Now, other question is, somebody has asked me a question, what is carbon-13 NMR spectroscopy? All right. See, whoever asked this question, please remember, carbon-13 is also spin-half nucleus. Carbon has three isotopes: carbon-12, carbon-13, and carbon-14. Remember, in one of the classes, I explained to you, depending upon the atomic number and the atomic weight of an isotope of an element, we can find out whether it is NMR active or not. For example, carbon-12 you take. The carbon-12, atomic number is 6, atomic weight is 12. Both are even numbers. When both atomic number and atomic weight are even numbers, that means the spin of such nuclear spin is 0. They are not NMR active at all. As a consequence, carbon-12 is NMR inactive. It is called NMR silent nucleus. You will not be able to see carbon-12 NMR. Whereas carbon-13 NMR, if you consider, atomic number is 6, atomic weight is 13. As I told you, remember, in the 1 or 2 classes when I was discussing chemical shift, I already told you, even before, while introducing NMR, I told you, for atomic number, when the atomic weight is odd number, the spin of that nucleus is half integer. So carbon-13 has spin half. So we can detect the carbon-13 NMR. Consider a molecule which has both carbon and proton. Take an example of chloroform, CHCl3. Forget about chlorine. We consider carbon and proton. Proton has spin half. If you see proton NMR, get a peak for proton. If you see carbon 13 NMR, that is, you set the resonating frequency pertaining to carbon, you get a signal from carbon, not from proton. It's a simple molecule. Take a very big molecule, organic molecule. It has both, it has carbons and protons present. If you do proton NMR, then you will identify you will get the peaks pertaining to protons. Chemically inequivalent protons, you get different peaks. Similarly, if you do carbon 13 NMR, for chemically inequivalent carbons, different carbons, you get different peaks. So assignment of proton peaks will tell you more about the protons. You can get information about the proton skeleton of the molecule. Assignment of carbon 13 NMR spectra, using that you can assign find out the carbon skeleton of the molecule. Using both proton spectra and carbon spectra, you can get structure of molecule containing only carbon and proton. This is an advantage. So carbon 13 NMR is nothing anyway different. Only thing is everything is similar to proton, but the resonating frequency corresponding to carbon. But of course, there are several differences are there, which I'm not going to explain now. But you can see it is in the class. I've discussed all those things. Yet again, I'm telling you, if you have any questions, if you don't understand, we can make a video call. I'll share the PowerPoints and explain to you very, very slowly so that you can understand. Are you all with me? Yes or no? Did you understand? All right. So, who asked this question? Okay, one person by name 9773667 number. So that person, please tell me, have you understood this or not? If you understood this is fine. Otherwise, please call me. I'll explain to you more in detail, but call me sometime in the afternoon or something when I'm free. I can, it will, because it will take more than half an hour to 1 hour to explain. When I'm free, I will open the PowerPoint slide and explain to you. Call me sometime later. Are you all okay? Please respond. I should know whether you're understanding or not. Any other questions?
You're on mute, sir.
So many people have joined. Jadhav, Mayuri, Nikita, Pranav, Sanjana, Simran, all of you, please ask me if there are any questions because the time is getting over, session is getting over, we may have to close it. If you still have questions, please ask me immediately. If there are no questions because the time is up, NPTEL office is going to close it.
Thank you, sir.
You have any questions, madam? Okay. So what do we do, Bharat?
We can close the session, sir.
Okay. Thank you all of you for joining. If you have any questions, call me or send me mail. We will now close this session because time is over. They have to start somebody else's live session again. Thank you all.